There are four main types of motor starter that we have to consider. I'm going to cover two of them here, and the other two, as well as these, are covered on your handout, as well as the video which I've posted on Teams. So this is the direct online starter, and the clue is in the name. Here is our motor that we're going to start, and we literally connect the supply straight to it. There is no delay, there are no form of steps, there's nothing to gradually start the motor up, it's full supply or nothing. So it's direct online. So here is the motor with the modern terminology for the windings, U, V and W. Over here I have the circuit isolator, and this is the contactor coil. The contactor coil, when that is energized, will close or open the contacts on the contactor, and that's what these are meant to show. So in plain English, if I close this isolator and we could close these contacts, then this motor will be energized and it will run. So let's have a look at how we do that. The first step is we need to get 230 volts to the contactor coil. So one end of it is going to be connected to neutral. So we need to pick up a live plus a start button and get it over to this. So literally we take it from here and we're going to go up there, and I'm going to introduce the start button, and the start button is normally open. So there is my button. And if we just stop at that for a moment, we can just consider what's going to happen. If we close the isolator, that has put the supply onto the system, but not to the motor yet. If we close this switch, this button, apologies. If we close that button, that's the start button, then we then have 230 volts, just one phase, up to the contactor. The coil will energize and all of the contacts associated with this contactor will now be energized. So if they're open, they'll close. If they're closed, they'll open. So in short, these contacts will close. When I've pressed that button, these contacts close and the motor runs. So what happens when I take my finger off this button? It'll be a spring-loaded button. So if I take my finger off it, I immediately open the circuit again, and in opening the circuit, this will de-energize, these contacts open, and the motor stops. So that's not very good. So how we deal with that is, on the contactor, there's more than just 3 sets of contacts. There are auxiliary contacts, and one of them we'll use to connect in parallel to the start button. So let's colour it in red because it's tied to that. So this will be called a hold-on contact. And if we follow what happens now, we press the start button, this energizes and all of the contacts are engaged. So these 3 close and the motor runs, but also this one closes. So when I take my finger off this, the supply will continue through here to keep the contactor engaged. Okay, so that's got the motor started and we have a hold-on contact. The next thing we need to think about is, how do we turn it off? So to turn it off, we need to insert a stop button. And I've had to fiddle with a piece of paper to do this, but here we go. Here's a stop button. So our start, which is this one, is normally open, and the stop button is normally closed. Oop. Fingers are sticking to it. There we go. So the stop button is normally closed. So if we're in the situation where this contactor is energized and all of the red contacts shown here are closed, then the motor will be energized, it will be running. To stop it, we need to disconnect the coil. And to do that, we have a normally closed switch or a normally closed contact in series with the coil. So when we press the stop button, we break the circuit to the contactor coil. That will de-energize every contact, including that one and these, and the motor will then stop. So this has the advantage that the motor cannot accidentally be restarted, which is called no volts protection. If someone was to just press the stop button and then let go of it again, the motor will stop. It will not restart automatically because this contact has opened. Okay, let's just have a think about that in one simple diagram. Let's look at that. Okay, so what we've just done is we've turned on the full supply straight onto the motor in one step. So I'll attempt to draw this. There we go. So from t equals 0, we put full supply on the motor and it will run at its full speed. So it's just a one-step process. The next step going on from that is to use a two-step process, which is called a star-delta starter. And I'll come back to my little graph in a moment. So just some reminders about star and delta. In star, if we have a 400 volt supply, which is what we would have for a three-phase motor normally, so there's 400 volts there, then we get to 30 volts across each phase. So what we're going to do with a star-delta starter is use an arrangement of contactors to initially put 230 volts across each winding, which means the motor will wind up to around about 58% of full speed. At that point, there is a changeover of contactors and the motor windings are rearranged into delta. And at that point, we get the full 400 volts across each winding. So we have a star-delta starter. Step 1 is 230 volts. Step 2 is 400 volts. So just to put that back on my master diagram, we're going to start in two steps. Firstly, start in star, and then a tiny delay, and we'll change contactors and we'll go on to delta. So this is a star-delta starter. And the red one was direct online. Okay, there's much more detail on your handout about the star-delta starter. Please read it carefully. So the third one is a rotor resistance starter, and this is covered in the video which I've posted online. The rotor resistance starter uses a wound rotor motor with slip rings, and resistance is connected to the slip rings, and we use that to slow down the starting process. So with a rotor resistance starter, we can gradually speed up the motor. So this is rotor resistance. Again, you'll find that on the handout. The fourth and final one that we need to be aware of is electronic motor starting. With electronic motor starting, often called soft start, we can use electronics such as thyristors or triacs to control the speed. We control the amount of current that is delivered to a motor, and we have total control. And I could represent it in many different ways, but the simplest way is just something like that. So on Teams, you'll find a version of this, and you can just label it up as per.